In this video, we're going to look at how we can model oscillation in 1D. I know that in our previous work, as we were thinking about 1D systems, we had talked about how it wasn't actually possible to get oscillation in those systems. Let's recall the argument actually. Let's think about a system x dot equals f of x. Here I've drawn a sample for what f of x might be. Recall that this is telling us about the velocity of our particle at a particular value of x. So if I'm at x naught, the velocity of my particle when I'm at that position is given by this function, and there's only one possible value to this velocity. If I think about possible solutions, so solutions are functions x of t that tell us how our state depends on time, well, every single time I pass through x naught on any particular solution curve, I always have that same velocity that we were given by this definition over here. And so if I have that velocity, whenever it is that I pass through x on a particular solution curve, I'm always going to pass through it going at the same speed and going in the same direction. In this case, the velocity is positive. I'm always going to pass through increasing and always increasing at the same rate. So there's no possibility of oscillation because every single time I hit this value of x, I'm always going upward. And that means I can only hit it once. I can't come back down through it. That would imply that some other time when I got to this point x, I had a different velocity, which isn't possible. How will we get around this so that we are actually able to model oscillation using a 1D system? We'll get around this by actually building oscillation in as a possibility for our variable. The way that we'll do that is we'll replace our x variable, which ranged along the real line from negative infinity to infinity. We'll replace it with an angular variable, theta. With this particular variable, 0 and 2 pi and 4 pi and 6 pi and 8 pi, they're all going to be identified with each other. And so we're actually going to think of this variable as sitting mod 2 pi. So theta mod 2 pi is our angle, or often something that we call the phase of our system. So we have a system, and theta is telling us kind of where we sit on this system. An example where we're really used to talking about phase is actually the phase of the moon. And so I'm going to think of an angle of 0 as corresponding to a new moon, and an angle of pi over 2 as corresponding to a waxing half moon, so like we're seeing more and more of the moon, an angle of pi as corresponding to a full moon, an angle of 3 pi over 2 corresponding to a waning half moon, so we're in the process of shrinking at the moment, and then getting to 2 pi, which is the same as returning to 0, we're back to the new moon. So in this sense, our number theta is telling us where we are in this lunar cycle. A very simple system would be theta dot equals omega. So this is a system where the angle is simply steadily marching along in time. The solution to this system would be that theta of t is equal to omega t plus some arbitrary constant. And so what's happening in this system is just as we go forward in time, let's say we set our constant to 0, and our initial time is 0. Then at time 0, here we are at the new moon. And as we go forward in time, when omega t is equal to pi over 2, we'll be at the half moon. When omega t is equal to pi, we'll be at the full moon. When omega t is equal to pi, we're back at a different half moon. And when omega t is equal to 2 pi, or 4 pi, or 8 pi, etc., we're back at the new moon. The period of this system is however long it takes for us to return to the new moon. In this case, that happens when omega t has gone from 0 to 2 pi. So every time omega t increases by 2 pi, we're back at the same phase. If we start here and omega t increases by 2 pi, we're back here. So the period is the amount of time t, the elapsed time that it takes so that omega t is equal to 2 pi. In this case, that period is 2 pi over omega. 2 pi over omega. And for the moon, I guess it takes, I don't know, it takes about 28 days to go through this cycle. So we want this period, 2 pi over omega, to be about 28 days. And then that actually determines for us what omega is. If we want 2 pi over omega to be 28 days, then we should be able to find omega without a problem. Okay, and so the way that we've gotten around the fact that we can't have oscillation in a 1D system is that we've changed to a different variable that is intrinsically designed to be able to encode oscillation. So that was kind of a nice trick, actually.